Hello and welcome to the 16th lecture in this series. In my last lecture, I had stopped at, towards the end of the lecture, we had discussed the derivative or differential of a smooth map between manifolds. And this turned out to be, if you have a smooth map between manifolds, then the differential at P turned out to be a linear map between the tangent spaces, which we still haven't proved are finite dimensional, but that's not needed to talk about the derivative. Now, in fact, to talk about, to prove that the tangent space is finite dimensional, I'll need to talk a bit more about differentials of smooth maps. Then we'll all put it all of the various things together and get the finite dimensionality. Properties of the derivative slash, sometimes I'll say it's the derivative, sometimes it's a differential, it's the same thing. The first thing is that the chain rule. So I have three manifolds, M, N, and X. So let's say I have G and F, two smooth maps. So if P belongs to M and F, G are smooth on M and N respectively, then G composed with F from M to X is smooth at P. Once we know the maps as this map is smooth, I can talk about its derivative. DG composed with F at the point P would be a linear map from TPM to TG composed with F of P at X. So let me write it like this. DG at F of P composed with DF at P. So there are three linear maps here, this left hand side and two maps on the right side. Now I said that G, so there are three tangent spaces as well, TPM, T F of P of N and T G composed with F of P of X. And this derivative is dg f of p, this derivative is dfp, and what we are saying is composing this dg with df at the appropriate points is equal to dg composed with f at the point p, which is a linear map from here to here. So I can go on. So this is a usual chain rule essentially, except that now we have to keep the big difference between this and the case of Rn is that we have to keep track of the tangent spaces where these maps are defined, the domains and images of these linear maps are important. Even though it's going to turn out that all these tangent spaces have the expected dimensions, and so we know from linear algebra that they're all isomorphic to Euclidean spaces of the appropriate dimensions. There is no what is called canonical isomorphism, natural isomorphism from different tangent spaces to Rn. So in other words, there's a choice involved in identifying a tangent space with the right Euclidean space. So this choice complicates things, and the thing is that if one regards Rn as a manifold, then at every point there's a natural way of identifying. There's a there is a natural way of identifying the tangent space at every point with Rn itself, which is not the case with an arbitrary manifold. So one has to keep track of this whenever we talk about differential. We have to keep track of the domain and range vector spaces. So this is the chain rule. The next thing that I need is that if I look at the identity map from M to M, so I is the identity, I of x equals x for all x. And if I look at the derivative of this at any point P, which is a map from TPM to TPM, this is the identity map again. If we start with the identity map between manifolds, of a manifold with from the manifold to itself, the derivative of that will be the identity map of the corresponding tangent space. And then so need this. Well, this is not exactly a property, these two properties. Usually these two properties that come, the behavior of a composition and what happens to the identity. If the expected things happen, then it's referred to as a functorial association. So associating a map, a smooth map with its derivative, has these two functorial properties, namely that the derivative of a composition behaves in the right way and derivative of identity is identity. The 3 is immediate, but let's do it anyway, since the definition of a derivative is somewhat abstract. So what do we have to check? Well, we look at the derivative dip is an element of TPM. Not quite. So dip is a linear map from TPM to TPM. So it should act on V, an element of TPM, and which that will act on a C infinity function. And by definition, this is V acting on. So I just have to go back to this notion of what I defined here. V acting on phi composed with F. So here F is identity for me. Phi composed with identity. Of course, anything composed with identity is itself, so I'll just get this. And so in other words, i.e. the derivation dip of V is the same as V itself. So since their action on for all C infinity, since their action on any C infinity function is the same, dip of V is equal to V. So therefore dip is the identity map on TPM. So here V is any T element of TPM. Right. Now, as for the chain rule, I don't know why small correction, I don't know why I put 3 here, there should have been 2. So let's say 2. So here 2. So now 1 is the chain rule. First, let's see that composition of smooth maps is smooth. So I have a F here and a G here, and I have a point P here. Now, according to our definition of smooth maps, I have 3 spaces, M, N, and X. So let's start with a point P here. According to our definition of smooth maps, smoothness amounts to saying that if I start with a point P, to say that G composed with F is smooth, I'll have to construct a chart around P and a chart around. So this point here is G composed with F of P. So I need a chart here and a chart here so that the map G composed with F in these local charts should be smooth as a map between open sets in Euclidean space. So now the way I construct these 2 charts is, of course, I'll just look at, I have to use the hypothesis on the smoothness of G and F. Since F is smooth, I'm assured of, I just have to write this a bit clearly. So this is P. Since F is smooth, I know that for any chart here and any chart here, the corresponding map is smooth, and similarly for G. Essentially, so I'll just start with, let's just start with some chart here. U, this phi will go to U1. And let's say this is W and the map is alpha. Alpha W1. So I'll just start with some charts here. And I want to look at alpha composed with G composed with F composed with phi inverse. That would be a map from here to here. So I'm interested in checking that this map is smooth. So what one does is something that we have seen earlier, namely you just sort of in this composition you put some so let me move on to the next page. It's getting a bit crowded here, and let me move this one a bit. So what I have is alpha composed with G composed with F and then phi inverse. So the idea is just that now there's a one missing point here which I have to now write down, namely this is G of P. So let me take any chart. I might have to modify it. For now, I'll just take some chart V around G of P and then a map, chart map C respect to V1. U1, V1, W1 are all open subsets of appropriate Euclidean spaces. Now, what one does is, so if one, in order to check that this is smooth, you just write this as phi inverse composed with, so instead of going, so this was G and this was F. Instead of starting here, going here and ending up here, well, actually not quite. So I'm starting here, going here, go all the way to the right side. So let me show it like this. So instead of going like this, which is what I'm doing here, I sort of take a detour. So I'll start here, go here, come here, then go down and go back up again, then follow G, and then the rest is the same. So in other words, I throw in this C and C inverse in between. So let me write it like this. So G composed with C composed with C inverse composed with F composed with, oh, I need a C. Yeah, this is fine. G composed with F. So I have to start with, oh, I put, sorry, I think I put it in the wrong direction. So it's actually, I have to start, phi inverse should come on this side and alpha should come on the other side. So to start with phi inverse and then alpha. Alpha is the last map. So I have to make a small change here as well. So I have to start with phi inverse, and then this does not come here. Start with phi inverse, then go via F, and then go via C. That's okay. For the next one, I start with C inverse, go via G, and then come via alpha. So this is essentially the idea. And the thing is that I know that F and G are given to be smooth, so therefore this is smooth, this is smooth, and the main point is that this notion of smoothness is just smooth in the usual Euclidean sense. After all, this is a map between open sets in Euclidean space, so is this. All three maps, the left hand side and the two maps on the right hand side, are all maps between open sets of Euclidean space. Therefore, we know that composition of maps is smooth. Now, the only thing which remains to be done is that one has to ensure as usual that when I want to do this C of, so F is going to land here, F of F is going to take this open set somewhere inside N. But in order to do C of F of, in order to do this composition here, I need to ensure that this open sets, these charts are chosen so that F of U is contained in V. Similarly, in the next stage, G of V is contained in W. So that can be done just by continuity considerations. So note not. So what one can start with, in fact, we can start with W. Fix a chart W alpha on X. Then you look at G inverse W, the inverse image of that is open in N by continuity of G, by continuity of G. Fix a chart on X, G inverse W is open in N. What else? Well, right, and contains, fix a chart, of course, this chart next around the given point G of f of P. And contains, so when I take G inverse, it will contain f of P, this inverse image of this set. There's something here in N. Since I get an open set, hence we can find a chart VC on N containing f of P, and such that this we can assume that this is contained in G inverse W. So when I take G of V, I'll safely end up in W. And once we have such a V, then I repeat the same thing with F. Now F inverse V is open in M, again by continuity, and contains P. Since V itself contains f of P, which I remarked here, we can find a chart U phi on M containing P, and such that U is contained in F inverse V. So F inverse V is some open set. Actually, the same process is repeated twice here. I'll just deal with F inverse V. We had to do the same thing for G inverse W as well. F inverse V contains some P. We know that. Now, if we want a chart which is contained in this open set, we take any old chart around P that might not be contained in V, but all we have to do is intersect that chart with the open set V, and we still get an open set which has the, so in other words, we still have a chart, but now that chart will be contained in V. It's a small thing that one has to do in order to check that these maps that we have, they are all well defined. But the main idea is you just throw in this C inverse and C, and that proves that. Now let me conclude by proving the chain rule. This was just regarding smoothness. Now the chain rule is it's a purely, since our definition of derivative is abstract, the proof of chain rule also is kind of quite different from the way one would prove chain rule in multivariable calculus. In my next lecture, I'll show that, after I show that this new notion of derivative coincides with the old one can regard this proof as giving a new proof of the classical chain rule. So the proof goes like this of chain rule. So I want to do dg composed with f acting on v acting on a function phi. This derivative is at the point p. Well, by definition, this is equal to, so again that picture, so m n x. So this is g, this is f, and g composed with f. And this function phi is a function on x. And v is a derivation as a tangent vector at m. So v acting on, so first I look at this function. This is just the definition of the derivative of g composed with f. Now what I do is, so I'll just write it as, okay, so this is the left hand side. Now let's look at the right hand side. Now let me look at the right hand side. The right hand side is in the chain rule would be dg at f of p acting on df at dg at f, dg df at p acting on v, whole thing acting on this function phi. So this is RHS. So on the other hand, this stuff here, again, what is this by definition? This thing acting on this is dfpv acting on phi composed with g. Well, phi composed with g is this map, and dfpv is something here, a tangent vector here. So I do apply the definition of derivative once more, and then I get, so this is equal to v of dfpv. So dfpv is something here, phi composed with g is a map on this. So I'll be doing phi composed with g composed with f, which is the same thing as, so phi I can just, composition is associative, it doesn't matter which order you write. So I end up with this, which is the same as what I started with. So this was the derivative of the composed map. That was this, and the composition of the derivatives is also gives the same answer. So it looks like we have not done anything at all. I mean, it's just a matter of algebraically playing around with symbols. But this is indeed the classical chain rule, as I'll show next time. So we'll stop here. Thank you.